Okay, so last time we got into organic chemistry. A reminder about organic chemistry. It's basically the chemistry of carbon type atoms. Really carbon and hydrogen. So organic really does deal with those kind of carbon bonds, carbon hydrogen bonds. Other sort of elements get substituted along the way, which makes up different sort of functional groups. Different functional groups basically represent different types of organic compounds that we see. A lot of the basis of organic compounds is sort of a non-polar relationship, carbon-carbon being a non-polar bond, carbon-hydrogen being a non-polar bond, and sort of how those guys sort of come together. It affects some of their properties of organic compounds versus, say, inorganic compounds like ionic compounds. They're a little bit different because of that. We talked about sort of the first real kind of class of organic compounds, which are alkanes. Alkanes really have the functional group of the carbon-carbon single bond as sort of the functional group. Again, a reminder that when we talk about functional groups in organic chemistry, it really is the part of the molecule that makes that compound a specific type of organic sort of molecule. So, for example, if we have all carbon-carbon single bonds, that is sort of an alkane. Those are really important in organic chemistry, especially the first 10 alkanes, as we talked about last time, has CN, H2N plus 2, N being the number of carbons there. Those first 10 alkane names, as we talked about, methane, for example, ethane, propane, butane, pentane, and continuing on in this fashion, hexane, heptane for 7 carbons, octane, nonane for 9, and decane for 10. These are really, really important, these first 10 alkanes, because all the way through the 10, because basis of everything else that we talk about in terms of organic chemistry, in terms of naming and all that kind of stuff, it's all based off of these first 10. So really important, again, as soon as you can, if you haven't done so already, you should make sure that you definitely know these formulas, how many carbons, how many hydrogens there are, and the names of these guys, because again, every single thing that we talk about will come back to these first 10 alkanes. So really important to know these guys, know their names, know their formulas, so that you pretty much can do everybody else in terms of naming and stuff like that. Again, the connection here is carbons to carbons, carbons attached to hydrogens. When we only have all carbon-carbon single bonds, they're sometimes called saturated hydrocarbons. Saturated hydrocarbons basically means that you have the maximum number of hydrogens to our carbon there, which is basically carbon wants 4 bonds, as we talked about. That's also a very important thing in organic chemistry. It wants those 4 bonds. So you want to always make sure when you kind of connect people, it's always carbons to carbons, and again, hydrogens to those carbons in most cases. Again, we'll substitute out hydrogen for some other things along the way, but this is a general sort of arrangement. This is what is referred to as the expanded structural formula that we talked about. This also can be written such as this, which is our condensed structural formula, or just condensed formula, most people call it. We also can draw random lines on the page. There, stop drawing. There you go. Get rid of that. Try it again. We also can draw a line structure, as we also talked about. Look something like this. Again, at each of these points are carbons, and again, enough hydrogens to get carbon to 4 bonds in each of those. So this is line formula, our line structure formula. And obviously for each of this guy would be C4H12 H10, which would be the molecular formula. And this obviously would be butane right here, would be the name of this guy. Now, we talked about these different structures. We also talked about towards the end there as well, a couple other important things are isomers. Isomers are basically the same molecular formula, but different connectivity. So isomers have the same molecular formula, but different connectivity, and by default, different names. So I think last time we ended with kind of looking at this guy here, C5H12, and you could draw some different isomers for us. So for example, I drew this guy, which is just this 5 carbons in a row, which is pentane. Here I decided to not go 5 in a row, but only do 4 in a row and attach that 5th carbon upwards. That gave me a different name, as we talked about last time, than pentane, which means these two are isomers of each other. The case on the bottom, I went actually 3 in a row and connected the other 2 carbons up and down there on carbon number 2, also giving me different name. These were all isomers of each other. We also talked about last time that when people go to draw isomers, they sometimes just want to, instead of doing again the kind of the 5 in a row, decide I'll just draw this guy down. Again, as we talked about before, if you sort of put all the hydrogens on there and go to name this, this will end up being pentane as well. Even though you drew it down, it is not a different structure. So very common mistake that people make is they think, well, I know, I'll just kind of make it look, you know, different. You know, like, hey, this definitely looks way different than the other, but actually it's still 5 carbons in a row, which would be pentane if you had nothing else attached there but hydrogens, and it would not be an isomer either. So just by drawing the thing different doesn't give you an isomer. You do actually have to have some different connectivities to allow it to be an isomer, and in order for you to actually have an isomer. Otherwise, you end up with kind of the same thing that you started with. Any questions on the stuff we talked about last time there? We also got into naming last time. And again, there's some general rules for naming, but we'll go through some more examples here in just a bit. But basically, when you talk about naming, there is sort of a pattern that you kind of want to follow. Basically, it's all about the longest carbon chain. And again, that longest carbon chain doesn't have to be the straightest. It could kind of go straight and then up and over. The only thing you can't do is backtrack. So if you go in one direction and go up, you can't come back down and go the other way. You got to kind of go in one direction until you hit like a dead wall and stop. And you want to check all your sort of ways of doing that to figure out what is the longest carbon chain. Once you do that, it should match one of these 10 alkanes. And that's sort of the base of your name. Once you do that, everything else attached will be what are referred to as groups. And groups are sometimes what are referred to as alkyl groups. And they are basically also, most of them based off of these 10 names. The only difference is they have one less hydrogen. And what that allows it to do is actually be able to bind into the main chain without having too many bonds. So because they're also oftentimes called alkyl groups, YL. So for example, instead of CH4, if we have a CH3 group, CH3 is based off of 1 carbon, which is based off of methane, dropping the last part of methane and putting a YL there, turns it into a methyl group. If we had like a 2 carbon group, CH2, CH3, this is the exact same number of carbons as ethane, and it has 1 less hydrogen. Again, that's where it's going to connect, and that is what is referred to as a ethyl group, propyl group, butyl group, pentyl group, and so forth as you continue down there. Once you identify the groups, it's all about numbering. You want to number the chain to give the groups the smallest number. And that's sort of what we did here at the end last time. Again, when you have a chain, say such as this guy, You could either number 1, 2, 3, going left to right for the guy in the yellow, or we could go 1, 2, 3, going right to left. In this particular case, it did not matter which way we went. Our groups were found on the same carbon, number 2, no matter which way you went. Now, if we went up here to this guy, we could go 1, 2, 3, and 4, giving our group at carbon number 2 here. If we went right to left, that would be carbon 1, that would be carbon 2, that would be carbon 3, and that would be carbon 4, which if we went right to left would give our group carbon number 3, which is a larger number than carbon number 2. So then we would go obviously in this fashion in terms of our numbering, as it gives our group the smaller number. Once we have that number, we attach it to our methyl. So in this case, this was 2-methyl, and then butane was the longest carbon chain, putting all that together. Groups go in alphabetical order there. And we want to put those guys a number. A couple other sort of key points when we do naming is in between a number and a letter goes a dash. If you have two numbers that are in a name right back to back, they are separated by a comma. So these are other sort of considerations that we do here. Any questions sort of on that naming aspect of it there? Okay. So let us continue on and talk about, again, when we talk about sort of groups that are attached to these guys, these are what are referred to as substituents, which is a fancy word for groups attached. They're basically groups that are not part of the main chain. So they are those guys that are, again, missing a hydrogen. If it's some type of carbon-based group, they're referred to as an alkyl group. They will end with that YL. If you have like a halogen, basically group 7, which oftentimes from the periodic table comes into play here, we name them fluoryl for fluorine, chloral for chlorine group attached, bromol for a bromine group, iodo for an iodine group attached. So these are common substituents that we see there. So here's a little table from your book of some of those substituents. And this is, again, a methyl group, a propyl group. There's a butyl group. There are some special sort of names for some groups. This is the isopropyl group. This group comes about a lot. This is an isobutyl group, also comes out sometimes as well. You may be wondering, this is a 3-carbon group. This is a 3-carbon group. So what is the difference between them? And the difference between them actually has to do with how we could classify carbons. And we could classify carbons as one of 3 ways: as a primary carbon, which has the symbol 1 with a little dot on, or circle on top; a secondary carbon, which has the 2 and the little knot on top; or a tertiary carbon, which has a 3 and a dot. And basically what those means is whatever carbon you're looking at, so we'll put a box around it, however many carbons are directly attached to that particular guy would tell you what it is. So looking at the guy in the box, he's attached directly to 1 carbon. So this guy in the box would be a primary carbon. If we look at a carbon here in the box as the one we're interested in, and it's attached maybe something like this. If we look at this carbon in the box, it's attached to 1 carbon, 2 carbons directly. This guy here would be what is referred to as a secondary carbon. And if we put a carbon there that we're looking at, and it's attached to, as you could probably imagine, 3 carbons, 1, 2, and 3, this is what is referred to as a tertiary carbon. And that's really where the difference is in each of these sort of groups here. These are both 3-carbon groups. These are both really based off of propane, for example. And if we drew out propane real quick, it will look something like this. And if we were to identify these carbons as primary, secondary, or tertiary, if we look at this carbon right here, attached to that carbon directly is one other carbon, which means that this carbon is a primary carbon. If we look at that carbon on the other end, also directly attached to one other carbon, would make it also a primary carbon, or 10 if you write it wrong, primary carbon there. But now let's look at the carbon that's sitting there in the center. And if we look at the carbon sitting there in the center, right there, we'll go with that guy. That carbon is actually attached to two other carbons, right? The carbon to the right, the carbon to the left. This is a secondary carbon. And it makes a difference in terms of how this group attaches to the chain. At this point, it needs to lose a hydrogen in order to attach. If it loses any of the hydrogens on the left-hand side off of that primary carbon, or it loses any of the hydrogens on the right-hand side off of that primary carbon, it will make this group right here, which is sometimes referred to as a N-propyl group or normal propyl group. Attachment occurs at the end at the primary carbon. But if we take off a hydrogen in the center carbon, which is the secondary carbon, any one of these hydrogens to allow it to attach, it will then make this group right here, which is the isopropyl group. And that's why we have a CH3, CH, CH3. The connection is happening at the secondary carbon. So that's how we get some different groups. This is like a historical sort of group and name, and we just roll with isopropyl just the way it is as terms of its name and how to name that particular group. Same thing here. This is a regular butyl group. If you look at this carbon at the end, it's attached to one other carbon. That's the primary carbon where it's attaching. If you look at the isobutyl, just like the isopropyl group, it is this guy right here. And a little bit different is, in this case, it's actually the 1, 2, 3, 4. So it's the tertiary carbon that's happening here in this case. And the attachment would actually be right here. That is not a right group. I don't think the way that is drawn there. So the attachment would actually be kind of into the center, guys. H should be at the end there, and it'll be more of an isopropyl, isobutyl group. So I don't think this would be the sort of right attachment, but it has the isopropyl sort of group there attached to it, so it makes it the butyl group. But the attachment will be here at this guy in this case. We'll go with it. I think it's right, actually. So we'll go with it. Again, it has sort of that isopropyl group attached to it. Just a weird way they kind of drew it there. All right, so these groups, most of them are based off of those first 10 alkanes. I would say out of the weird ones, this isopropyl is the one that probably pops up the most. You probably should also be maybe familiar with isobutyl, but most of the time, isopropyl will be kind of the only sort of strange one that pops up there. So let's take a look at this one and again, sort of see how we would go about naming this, just to review with you in terms of naming. What we're looking for is the longest continuous carbon chain here. And again, you want to try all of your options. So if we just go straight across, that is 1, that is 2, that is 3, that is 4. And since there's another option. You could go 1, 2, 3, and down for 4. Same option. 1, 2, 3, and down for 4. So really there's 3 different ways to get the 4. But I think, as I mentioned last time, if you have sort of a straight option, you might as well take the straight option. It's usually a little bit easier to kind of work with. So we have, if I could count correctly, that's actually 5 carbons in a row. Doing bang up business here today. 1, 2, 3, 4, 5. I think I could count. That is 5 carbons, which is our longest carbon chain, which means you should probably go with that straight one since it is the longest. That is pentane. There. Now, attached to this pentane, we have a Cl group, which would be a chloral group. We also have this one carbon group, which would be based off of methane, which is a methyl group. And what we would want to do now is number the chain. So we have two options. We could go 1, 2, 3, 4, and 5. The other option would be to number in the opposite direction. So we'll go this way in red, 1, 2, 3, 4, and 5. In terms of the red numbering, we would have groups at carbon number 3 and carbon number 4. That's where those groups are attached. If we went sort of the blue way in terms of the numbering, we have a group on carbon number 2 and a group at carbon number 3. So in comparison of what we're trying to do is we're really just trying to smallest number. So it is as simple as 2 is smaller than 3. So we would actually go the blue way here in terms of our numbering because it gives the groups the smaller numbers. Any questions on that? Because we chose the blue way of numbering, that means that the chloral group would be at carbon number 2. So that would be 2-chloral numbered to letter dash. The methyl group would be at carbon number 3. So that would be 3-methyl. All that's left is to put it all together in alphabetical order. So C before M. So that's going to be 2-chloral dash 3-methyl. And then the base of our name is pentane. Any questions on any part of that name, where it came from, or anything like that? So longest continuous carbon chain, put a box around it, highlight it, whatever you want to do. Circle all the groups that are attached to it, name those groups, number the chain, whichever way gives it the smallest numbers, the groups in this case, and then put them together in alphabetical order. Again, we have our dash between a number and a letter, same thing here and same thing here. All right, so that's how we go about sort of naming things that have groups on it. They're substituents for straight chain. We also talked about cycloalkanes last time. Remember, cycloalkanes are the same as straight chain alkanes, except it's missing 2 hydrogens because basically put the ring together, or the chain together in a ring form. So we had to lose 2 hydrogens to do that. If there is only one group attached, we would name that group. No need for number, because wherever the group would be carbon number 1. So in this case, the main part of this whole thing is a 6-member ring. So if you just kind of go 1, 2, 3, 4, 5, and 6. 6 carbons all in a row is hexane. In a ring structure, it is cyclohexane. And now what's attached out here is a group, and that is a 2-carbon group, which is based off of ethane. It's a ethyl group, and this would be known as ethyl cyclohexane. Question on that? If you did have more than one group attached, say like this, and let's go like that, you do need to give numbers. So in this case, the main part here would be the triangle, which is basically 1, 2, and 3 carbons. And that 3 carbons is based off of propane. It's in a ring structure, so it becomes cyclopropane. And now we have a chloral group and a methyl group that is there. Now, we could number this one of 2 ways. We could do kind of top to, or clockwise, I guess, starting at the top. We could go 1 and 2. We could start with the chlorine and go 1 and 2. Now, you may notice that they both give us the same numbers in terms of 1 and 2 or 1 and 2. We wouldn't want to go the other way, 1, 2, 3, right? Because that gives us 1 and 3, which is no good too much in terms of numbers. Which way should we choose? Well, since it's a tie in terms of which way you go in terms of the numbering, they both give you 1 and 2. The next most important thing would be alphabetical. So alphabetical, the chlorine would come before the methyl. So because in this option we do have that option, we would probably want to go this way in terms of the numbering, and that would give us 1 chloral, 2 methyl, squeeze it in, methyl cyclopropane. Any questions on that? So if you have just one group attached to a cycloalkane, no need for numbering, because it's assumed wherever that group is located would be carbon number 1 on the ring. If you have multiple groups, again, you want to go whichever way gives those groups the smaller number, and that would be either clockwise or counterclockwise. And again, if it's a tie like we just had up there, you then would default to the next important thing, which again would be alphabetical order. Any questions on that there? Yeah. So let's then talk about the approach when we want to draw something from the name. So the approach always when you have the name and you want to draw the formula is very simply start in the back and work your way to the front of the name. As I mentioned maybe last time to some of you during discussion, this is sort of the easiest way out of the two, because it actually kind of tells you what you need to draw. So for example, let's take a look at what we see here. We see first off heptane. So what does heptane mean? Heptane means that is 7 carbons. So simply start out with drawing 7 carbons, nothing else, just the carbons. I'm going to try to count better than I did a second ago. 1, 2, 3, 4, 5, 6, and we'll go this way. We'll squeeze them through here. 7. Now that we have the 7 carbons, that really does take care of the heptane part. Nothing left there. 1, 2 dimethyl. So let's start with the dimethyl part. The di means that there are 2 methyl groups in this molecule. So we basically have 2 methyl groups. Where are those 2 methyl groups located? Well, one of them is located at carbon number 1, and one of them is located at carbon number 2. So remember, when we have more than one of the same group in a molecule, we do use a prefix like di, tri, tetra. Probably not more tetra, but di or tri in there. Maybe tetra in some cases. So where do we put these on the thing I just drew? Well, the good news is, since you are drawing, you get to choose which way you want to go. You can number it left to right, or you can number it right to left. I'm personally just going to go left to right. So that'll be carbon 1, that'll be carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, and carbon 7. So what does that mean? Well, I go to my carbon 1 and I slap in there a methyl group. And since I decided that this was carbon 1 for me, that means at carbon 2, I would put my other methyl group. You could draw them down if you wanted to. It does not make a difference. In this case, that takes care of that part of the name. So what is left? We have 1 chloral. So what is chloral? Chloral is a Cl group, and the 1 means it's at carbon number 1. So again, I go back to my drawing here, and I put in there my chlorine group. At that point, that takes care of that. What is left to do? Well, what is left to do is it's all hydrogens at this point. So let's get rid of these numbers here just to make it a little bit clearer. What do we need for hydrogen? Well, we need carbon to have 4 total bonds. So we put in the right number of hydrogens to give carbon 4 bonds. So this particular carbon, number 1, has a line coming in and 3 lines, other lines total, or 3 total lines, means he just needs 1 hydrogen. Carbon next to it, carbon number 2, also has 3 lines coming in, which means only needs 1 hydrogen. Carbon number 3 has 2 lines coming in, which means it needs 2 hydrogens. Carbon number 4 also needs 2 hydrogens as it has 2 lines coming in. Carbon number 5 there will need 2 hydrogens. Carbon number 6 will need 2 hydrogens. And carbon number 7 there will need 3 hydrogens. Any questions on how we do that? So always with the name, work backwards, start with just the carbon skeleton and kind of fill in everything as you go along. Any questions on that particular one there? Okay. So why don't you take a second here? Why don't you draw what it says there, 3-bromo, 1-chloral butane, and see what you come up with. Again, we have the names, so we want to roll backwards here. So butane tells us it is 4 carbons, so we just want to start with just the carbons. So that takes care of that part of it. 1-chloral means that a carbon number 1, I have a Cl, a carbon number 1. I'm going to call this carbon number 1 here, which means that is where I would put my Cl. That takes care of that part of the name. At carbon number 3, I have a bromol group, which is a Br. Since I called this carbon number 1, this guy would have to be carbon number 2. This guy would have to go to carbon number 3, and that is where I would put my bromine. At that point, everything else is hydrogen. Guy at the far end on the right needs 3 hydrogens to get carbon to 4 bonds. Now, carbon number 3 there needs just 1 hydrogen. I'm just going to get rid of the numbering there so it doesn't get too confusing here. So carbon number 3 there, again, just needs 1 hydrogen. Carbon number 2 in our numbering scheme needs 2. And carbon number 1 actually has 2 coming in, which means it needs 2 hydrogens. Any questions on that condensed formula there? Also wanted the line formula. So line formula, we will start with the carbons as well. That should be 1, 2, 3, 4. Again, same deal, because you're drawing, you could choose where you want to start with number 1. I will call this number 1 and put a Cl. That means, again, this guy right here would be number 2. This guy right here would be number 3. Should kind of be a straight line, but ish. There we go. Would be a 3. So the line structure would look something like this. Any questions on that particular one there? Okay. So take a second and why don't you name these guys? And while you're at it, let me add a few there, just a little extra practice here. Why don't we go with all right, so take a few minutes here, come up with the names for each of those, see what you come up with. Okay, let's take a look and see. So again, we're looking for the longest carbon chain here. Looks like actually it's just straight across is going to do that for us. So that is 1, 2, 3, 4, and 5 carbons. Means this is the main part of the chain. 5 carbons means the base of our name should be pentane. And we do have obviously a group attached here. And let's see, we have this group right there, which is a chloral group. So we have 2 ways to number. We could go left to right, 1, 2, 3, 4, and 5. Or we could go right to left, 1, 2, 3, 4, and 5. Again, we're always looking for the smallest in organic chemistry. So smallest number coming this way, right to left, means our group is at 2. So this would then be 2-chloral pentane. Any questions on that name there? All right, looking at the next one here. Let's see, we can go straight across. So 1, 2, 3, 4, and 5. I think that might actually be a winner there. 1, 2, 3, 4 if we go up. 1, 2, 3, 4, 5 if we go down. So might as well take the straighter one. And it looks like that is all your options, I think. So might as well just go straight across here. So this also, if I count it again, 1, 2, 3, 4, 5. So that is 5 carbons, which means it is also going to be pentane as the base of the name. We then have this group here and this group there. And again, you may say it just looks like an empty line, but remember at the end of the line is a carbon that has 3 hydrogens. So those are methyl groups, although that kind of looks like a G now, but it's actually methyl groups, each of those lines. So in line structure, if you just see a line with nothing attached, it's a methyl group. There are 2 methyl groups, which means we have dimethyl in the name because there's 2 of them. Now we need to determine which way we want to number this chain, going left to right. 1, 2, 3, 4, 5. Going right to left. 1, 2, 3, 4, and 5. So left to right gives us a group at 2 and 3. And going right to left gives us a group at 3 and 4. So again, we would want to go the other way because it gives us the smaller numbers. So that means 2,3 dimethyl pentane is basically the name here. So 2, 3, comma between 2 numbers, dash dimethyl, because there's 2 methyl groups in the entire compound, not on the same carbon, and pentane. Any questions on that name right there? Okay, then rolling through here, I'm thinking straight across is going to do us longest carbon chain. 1, 2, 3, 4, 5. Could also get it started on the bottom. 1, 2, 3, 4, 5. But again, might as well take the straightest. So it looks like pentane is the winner for this slide. So pentane again, not always going to be pentane as the base of the name here. We got a chloral group here and a methyl group here. And in this case, you could probably just see it going left to right here will give us the smaller numbers. And that means that actually both groups are at carbon number 2. So we do want to go alphabetical here. So this would be 2-chloral dash 2-methyl pentane. Any questions on that there? Okay, that leaves us the big guy there. That is a ring structure of 6 carbons. That is obviously the main part of it. So that would be hexane. And because it's a ring structure, and you want to spell hexane right, I suppose, it would be known as cyclohexane. It also has 2 groups. It has one group here, which is just like what we saw over there. That is, again, a methyl group. And what about this group over here? That is 1 carbon and 2 carbons. That is an ethyl group in this case. We can number a couple of ways, but you might want to start with the ethyl since it's alphabetically first. 1, 2, and 3 in that case. If you went clockwise, it would be 1, 2, 3, 4, 5. So obviously 1 and 3 counterclockwise here is good for our numbering. That gives us a 1 ethyl, 3 methyl cyclohexane. Any questions on where any of those names came from? Okay.
Professor, I do
Yeah.
have
Yeah.
If you okay, so if we have like right here, we have two of the functional groups, the methyl and the ethyl,
Mhm.
on the ring on the cyclohexane.
Mhm.
So whenever we have a situation like that, do we always have to start counting from the one that comes like first in the
In terms of like alphabetical.
yes.
You don't, but in this case, so in this case, I didn't do the two options that we had, but because the groups, I won't draw the groups. Oh, I'll draw them correctly, I guess. Because the groups were here, we had basically two options. We could have started with this guy and went 1, 2, and 3, and we could have started with this guy like we did and went 1, 2, and 3. And no matter which way you went, they both gave you the same numbers, 1 and 3. So in that case, it's kind of like that tie we had earlier. Then the next most important thing would be alphabetical. So that's why I kind of just started numbering from the alphabetical guy, because I could see that it would give me the same numbering no matter which way it went.
Okay, thank you.
So to answer your question, you do want to go smallest numbers first, but again, in a situation where you get kind of a tie no matter which way you go, then you want to kind of go to the next important thing, and that would be alphabetical.
Okay, thank you.
You're welcome. Other questions? Okay. Then let's do actually just a couple more formulas from names. Let's do propyl cyclobutane, and let's do 2,4 trichloral pentane. All right, so draw the condensed structures fine for each of these. Let's see what you come up with. Name, and you need to draw the formula. I think it's the easier thing. We're going to work our way backwards. So the first part of it is cyclobutane. Butane is 4 carbons. Cyclo means a ring structure. So you would do your 4 carbons. This is the guy that looks like a square, basically, like that. That takes care of this. Propyl means we could put it anywhere you want. It's assumed to be carbon number 1 since it's the only group. I'll just throw it here. It doesn't really matter which one you put it on. That is a 3 carbon group. So it'll look something like this. Oops, 2 and then 3. Rest, just like in the straight version, is hydrogen. So this guy needs 2. This guy needs 2. This guy needs 2, and this guy just needs 1, basically. So it'll look something like this here. Again, more line structure will look something like this here. Any questions on that one? Or even all line structure would look like that. One more up. All right. Then doing the same approach here for backwards is pentane. So that's going to be 5 carbons in a row. That takes care of that. I got a trichloral, which means I have 3 of these chlorines. And where are they located? Carbon 2, and carbon 4. I'm going to number left to right. That means this is carbon 2 for me. That's a chlorine. That's a chlorine. That takes care of that guy and that guy. And since this is carbon 2, this would be carbon 3. This would be carbon 4. Takes care of that guy. And now what's left is hydrogen to get carbon to 4 bonds. Guy at the end needs 3. Guy right here needs just 1. This guy has 2 lines coming in, means it needs 2. This guy has 4 lines coming to it, which means it is done. And the guy at the end needs 3. Any questions on how to go from name to formula? All right. Any questions on how to name alkanes, basically?
So the second carbon doesn't need a hydrogen attached?
This guy right here, this carbon, like right.
Yeah.
Okay. No, it doesn't, because if you count how many are attached there, even though I kind of I left a lot of space between the lines, but if you count it, it's got 1 coming in here, it's got 1 coming in here, it's got 1 coming in here, and 1 coming in here. So it has 4 bonds already, so it's good to go. Other questions on that? Again, Sometimes when you leave a lot of space, you could close the gap a little bit like that. So you guys see, there we go. Yeah, so the goal, right, is to get carbon to 4. And in that case, he had actually 4 to begin with, so he doesn't need any more. Other questions? Okay, so those are alkanes. Obviously, you need to be able to give the name if you got the formula, or from the formula, give the, I say that right, I think, give the name from the formula, or if you have the name, draw the formula. And for alkanes, cycloalkanes, with and without things attached. You're welcome. All right, so just to conclude on alkanes, some properties of them. Again, alkanes results from their physical properties, including solubility and density, because a lot of them are nonpolar. Nonpolar doesn't work very well with water, so kind of like wax and stuff like that. You know, it helps retain moisture because water and organic guys really don't mix very well together. Alkanes with 1 to 4 carbons are typically gases at room temperature. So a lot of those, like our methane, propane, butane, you know, you're probably familiar with, right? Where you barbecue and all that in your gas tank and all that kind of stuff. Alkanes of 5 to 8 are highly volatile liquids at room temperature, making them useful as fuels like pentane, hexane, heptane, octane. Octane, like when you fill up your car, right? 91 octane and all that kind of stuff, right? That's basically what you're doing. What does volatile mean? Volatile means it can go into the gas phase very easily. It goes into a gas phase very, very easily. So something is very, very volatile. It's able to kind of go from liquid to gas very, very quickly without a lot of convincing and stuff like that. As we get kind of higher, 19 to 17, these guys have much higher boiling points, like motor oil, kerosene, diesel, so decane with 10 carbons. Alkanes 18 or more are known as paraffin, so wax, petroleum jelly, Vaseline, or they're 25 or more sort of carbons. We get all these different sort of products by what is sometimes referred to as fracking. You basically take a big long chain of organic compound carbons and hydrogen and basically break them apart into smaller segments. And these smaller segments gives us some different sort of properties associated with them. You know, like breaking it down into sort of gasoline, breaking it down into, you know, sort of butane, propane, and those type of fuels. Alkanes, again, because of that carbon-carbon bonds, which is nonpolar, carbon-hydrogen bonds are nonpolar. They're basically insoluble in water. They're less dense than water. I think we talked about it last time. If you mix water and an organic compound, that's usually your organic guy up there on top layer. Bottom layer is usually your water or aqueous layer is usually on the bottom. Again, very flammable. Obviously, a lot of organic guys are. What type of reaction do our alkanes undergo? They undergo one that we've seen before, and that is a combustion reaction. And that's an organic combustion reaction. Remember, we have our organic guy here, carbon, hydrogen, sometimes oxygen. O2 on the left-hand side always makes CO2 and water. So in an organic alkane type combustion reaction, those are definitely the ones that we always get. We get our CO2 and water as our product whenever you do a combustion of an alkane. O2 is always on the reactant side there in its molecular form, or in its molecular natural form of O2. And that's a very common sort of reaction that alkanes undergo. Here's an example of, you know, butane going through a combustion reaction. Again, we see O2 on the left, products of CO2 and water. That means heat, and usually gives off energy. So you think like lighting a Bunsen burner, for example, or your natural gas sort of stove, right? You get the flame and stuff like that. And that's basically all you need is a spark, basically, and it will happen. Propane, the same deal as well. Again, here's our balance equation, just like normal chemical equations we talked about. We want to make sure you go through balancing them. Don't forget, a lot of times with these guys, you know, we had to use a fraction sometimes to balance them. So that's a common sort of reaction that alkanes undergo. So O2 combustion reactions, CO2 and water, always the product that you'll make. Another type of reaction that an alkane will undergo is one is referred to as a substitution reaction. And in this case, you could take an alkane plus a halogen and some heat or some light, UV, and you will get basically what is known as a substitution reaction. In a substitution reaction, much like the name implies, something comes off and something comes on in its place. So from the alkane, off comes a hydrogen, and on comes a halogen. One halogen comes on. So let's see how that works. So if we had, say, this guy right here, which is ethane, and we react ethane with like bromine, for example. Remember, bromine's a halogen, it comes as a 2. We could choose any one of these hydrogens we wanted to come off. They're all what are referred to as being equivalent with each other. They're basically all the same hydrogens. Doesn't really matter. So what's going to happen is one of these hydrogens will come off, and only one of these bromines will come on in its place. Absolutely, positively, when we're doing organic chemistry and reactions, absolutely, positively, nothing else changes. There's just one spot of the molecule that changes. Everything I'm highlighting in green stays absolutely the same. So the nice thing about these type of reactions is you pretty much have most of the molecule already drawn for you. You pretty much just need to copy what's there. So you can see here, I copied exactly what's in the green over. The only difference is I did not copy the last hydrogen because it came off, and we're going to replace that last hydrogen with the Br. Now let's talk about what came off. We came off a hydrogen, which is really an H+. And what do we have left over here? We have another bromine. These two guys will actually come together and make hydrogen bromide. This is what is referred to as monosubstituted product. Monosubstituted product means one, which means we put one halogen on. If you let it go forever, every single hydrogen will be replaced. But if this asks for the monosubstituted, pretty much just pop off one hydrogen, put one on. Doesn't matter if it's a ring structure like cyclohexane, doing the same thing here. Although not drawn, there's 2 hydrogens at every one of these carbons. So same thing, one goes off, one goes on in its place. Absolutely nothing changes about the ring. And this is something important to remember. Nothing weird happens like it opens up or anything like that. We put the bromine on, and just like above, the hydrogen that came off hooks up with the second Br that is there. So just for a reference point here, this guy is this guy. This hydrogen coming off is this hydrogen over here. And then obviously this bromine right here is this guy coming on. So that is sort of what's happening. Same thing here. Again, this hydrogen coming off is going to hook up with that guy. And this guy was this hydrogen here, our bromine there. Any questions on this substitution reaction? Important on these reactions, really just to remember generally what happens. As I mentioned, it's sometimes very hard for a lot of students to get that point. They always want to think, well, it's organic chemistry. It sounds very hard. There must be some weird, all kinds of all over the place reactions happening. Things should be breaking. We should be making a whole bunch of stuff. It really doesn't. Things stay the same. As you can see, this entire thing stayed the same. Nothing changed. Just that one spot. And it's always just that one spot in most cases that changes, and everything else stays the same. Any questions on alkanes and the reactions? Okay, then let's talk about some other organic compounds, which are alkenes and alkynes. Alkenes have a functional group of really the carbon-carbon double bond. Alkynes have the functional group carbon-carbon triple bond. So these are what are referred to as unsaturated. Hydrocarbons. Why are they unsaturated? Well, they contain at least one double bond or a triple bond, which means they do not have the maximum number of hydrogens allowed, if you will. Alkenes, because of that, have the general formula of CnH2n. So if you remember, our alkane was H2n plus 2. Because we put that double bond on, we lost 2 hydrogens. Alkynes have the general formula of CnH2n minus 2, actually losing 2 more hydrogens in that case. And basically every time we put on a hydrogen, a bond, we lose 2 hydrogens. So here 2 carbons, 2 times 2 is 4, minus 2 is 2 hydrogens. This is ethine. Where's that name come from? Well, if we take a look at this guy, and we take a look at this guy that we just drew, this is 2 carbons, all single bonded. That is ethane, A-N-E, because it's an alkane. 2 carbons based off of ethane, but has the double bond, becomes ethene, E-N-E, because it's a alkene. C2H2, as based off of ethane, but has a triple bond. It is known, as it says there, as ethine, Y-N-E, because it's an alkyne. So the kind of name of the functional group is sort of how we go about naming these guys based on where they have sort of double bond or a triple bond. Again, hopefully you can see it is going back to our first 10. So really important to get those names down. Alkenes and alkynes, as I mentioned before, they have double bonds or triple bonds. They are going to be unsaturated because of that, because they basically will lose 2 hydrogens for every bond that they make. So that double bond loses 2 hydrogens, triple bond loses another 2 hydrogens. They react with hydrogen gas and a number of hydrogen atoms to become alkanes, as we'll talk about in a reaction a little bit later on here in this chapter. Alkenes, because they do have that double bond, also changes its geometry of alkenes. It now has, when we look at the central atom, 1, 2, and 3 electron pairs, and also 3 bonds. It has the trigonal planar geometry, which is why it has a bond angle of 120 degrees because of that double bond. It is different than the tetrahedral arrangement that we see with alkanes. So be adding that double bond changes the actual geometry. You don't get that kind of zigzag shaped so much because of that double bond that's happening. This is ethene, again, sometimes commonly called ethylene, but most people call it ethene. It's important in plant hormones, accelerates the breakdown of cellulose in plants. Alkynes, on the other hand, like I said before, has that triple bond, also based off of, the ethane, and has 2 carbons, and again becomes ethine. What happens with its bond angle? Well, its bond angle, as we go from ethene to ethine, becomes linear. It has 1 electron pair, 2 electron pairs, and 2 bonds. That is our linear, our 180 degrees. So again, as we put on the 3rd bond, everybody is flattening out into a linear geometry. So I think somebody asked a question the other day about that. As you can see, as we add these double bonds or triple bonds, it does affect the way that the bond angle ends up being, because we have those different bonds that are occurring. Any questions on that there? And again, every time we put that bond, we lose 2 more hydrogens off of the alkane. Identify the following compounds as either an alkene or an alkyne, and these are some line structures, and you can kind of see how you incorporate into a line structure the double bond and the triple bond. Here it actually is a double bond, right? So this would be an alkene because it has the carbon-carbon double bond. The guy below it would then be an alkyne because we have a triple bond happening right there. And this guy would be an alkyne. Any questions on that identification there? Okay. So how do we go about naming these guys? Well, they are pretty much named similarly to how we go about naming alkanes. The difference, though, is in this case, if it's an alkene, it will end in ene. If it's an alkyne, it will end in yne. The other difference is how we go about numbering the carbons. If you remember, with alkanes, we number the carbons in a way that gives the groups attached the smaller number. Here, when we have either a double bond or a triple bond, they take the priority, which means that they need to have the smallest number. So when we go to name it, we want to make sure that either the double bond or the triple bond ends up with the smallest number, and everybody else would be named accordingly. So for example, if we back it up here to this one that we were just looking at, let's take a look here. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. 8 carbons is based off of octane. It has a double bond, so octane becomes octene, ene, because of that. Now, there's no other group attached, but we do want to give the location of where the double bond is at. And that happens when you have more than one option for where it could be. In this case, there's more than one option. If we number left to right, 1, 2, 3, 4, 5, 6, 7, 8. If we go right to left in terms of the name numbering, this would be 1, this would be 2, this would be 3, this would be 4, this would be 5, this would be 6, 7, and 8. The goal here is just like before. We want to go whichever way gives, in this case, the double bond the smallest number. That means a double bond starts at carbon number 3 in the blue way, starts at carbon number 5 in the red way. We would want to go with carbon number 3 there since it is smaller. This would be known as 3-octene. The 3 is the location of the double bond. Ene is because it has a double bond in it. Octene because octane is 8 oxygens or carbons. Any questions on that? Let's take a look at the bottom one here. Well, when we number or find the longest carbon chain, it does need to contain the double bond or triple bond. So we go straight across. That's 1, oops, come here, 2, 3, 4, 5, 6, and 7. If we went 1, 2, 3, and then down, 4, 5, 6. So it looks like straight across is the longest carbon chain that does contain the double bond or triple bond in this case. So 1, 2, 3, 4, 5, 6, 7. 7 carbons from the alkanes is heptane. Because it has a triple bond, we get rid of the last part and it now becomes heptyne. We now want to number the chain here. So this would be carbon 1, this would be carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. If we go the other way, this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, and carbon 7. Again, we're looking for the triple bond to take the priority. So priority-wise, triple bond is at carbon number 1, which means this would be 1 heptyne. That is the location of the triple bond. Now, because I chose left to right in terms of my numbering, I have to stick with that for everybody else that's there. That means that I do have one other group here. And that group is that guy hanging down on the bottom there, which is here. This is a 1 carbon, 2 carbon, 3 carbon group. 3 carbons, that's a group. That is a propyl group. And because the triple bond is carbon number 1, that means that that group is at carbon number 3. This would be 3 propyl, 1 heptyne. Question on how I got to that name. All right, so let's take a look at a couple more here. Why don't you take a second here and name each of these, see what you come up with. Here, so same approach, we're going to be looking for our longest carbon chain. Again, it does need to contain the double bond as we see the double bond there. So in this particular case, there's actually a couple different ways you get there, but we could go straight across 1, 2, 3, 4, 5. You could also go down here as well, go 1, 2, 3, 1, 2, 3, 4, 5. But again, might as well take the straightest just to make it easy. So that is 5 carbons. That's going to be based off of pentane. It has a double bond, so my ANE now becomes pentene. I need to give the location of that double bond going left to right, 1, 2, 3, 4, 5, going right to left, 1, 2, 3. So if you went this way, the double bonds at carbon 3, if you go left to right, double bonds at carbon 2. So we would want to go this way in terms of our numbering, giving our double bond the smaller number. So that is 2 pentene. Again, the 2 representing the location of the double bond. Because we locked in that way of numbering, that means our group right here is located at carbon number 4, and that is a methyl group. So that'll be 4-methyl 2-pentene. Any questions on that one there? All right, coming straight across here, we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. You can see how it really straightens out there the triple bond in our line structure. So you don't want to miss the carbon on either side of that triple bond. So that is 1, 2, when I count there, 3, 4, 5, 6. 6 is based off of hexane, has a triple bond. Hexane becomes hexyne, YNE. Location of that triple bond, you could probably vision going this way is the shorter route. That's going to be 2-hexyne. Any questions on that? All right, so just to finish up on, since we also need to be able to go from name to formula, we would approach it the same way. So we'll do this one here together to finish up on. So pentene tells us again that it is 5 carbons, and you could just start with the 5 carbons. ENE tells me it's a double bond, and that double bond's located at carbon number 1. So double bond carbon number 1. I'm going to call this carbon number 1. So I'm going to turn that into a double bond. That takes care of that whole deal. Because I called this carbon number 1, that means when I go to carbon number 3, I should have a methyl group there. And because this is carbon 1 for me, carbon 2 would be next to it. Carbon 3 would be right here. And that would take care of that. Just like the alkanes, everything else going to be hydrogens to get carbon to 4 bonds here. And this guy would need 2. So you would work name to formula the exact same way as we did the alkanes. Just put in obviously your double bond or triple bond in the right location. And then whichever way you did that, that's the numbering you use for any groups attached. Question on that? Okay, we will lay it up there today. One last thing is we do have an exam coming up in a couple of weeks, I think at least, and it's on some live chapters 9, 10. So it's been a while since we talked about 9, which was solutions. So I think what we'll do is next Monday, we'll take a quiz on chapter 9, which is solutions. Be a good review for the exam that will be coming up in a week or so after that. So we don't forget too much about that. That will involve calculations. So we'll do that on Monday at the towards the middle of lecture. Like normal, we'll stop early and you can kind of take it. Any questions on that? Just to make sure we don't forget about those chapters before the organic here with the last exam coming up.